Imagine waking up, right? And you step on the bathroom scale in the morning to just, check your weight.
Like we all do, yeah.
Right. But instead of telling you how your pants are going to fit that day, the number on that little digital screen tells you exactly how fast your brain is shrinking.
Oh, wow. That is a terrifying thought.
It really is. But today, we are looking at a medical reality that basically breaks the bathroom scale entirely. We're tossing out this whole idea that weight is just a simple matter of gravity.
Yeah, it's definitely time to move past that.
Exactly. Instead, we are diving into this totally mind-bending reality that the actual physical location of the fat inside your body might be dictating the physical structure of your brain, like the literal size and volume of your brain.
It really represents this profound paradigm shift, in how we view human biology.
Right.
We're moving entirely away from that old, tired question of just, well, how much fat do you have?
Which is what everyone focuses on.
Exactly. We're replacing it with a much more urgent biological question, which is, where exactly is that fat living?
Mm-hmm.
And what kind of biochemical warfare is it actively waging on your nervous system?
Biochemical warfare. I love that phrasing, even if it is a bit scary. So to guide you through this today, we have got a truly massive stack of source material.
We really do. It's a dense one.
Yeah, we are doing a deep dive into a groundbreaking 2026 paper published in the journal Nature Communications.
A very prestigious journal, I should add.
Oh, absolutely. And this comes from the FIT project, which stands for the Follow Interventions Trial. This whole thing was led by Daphne Pachter and a really massive international team of researchers.
Right. They were stretching from Ben Gurion University all the way to Harvard and to the University of Leipzig as well.
So a totally global effort.
Yeah, and the scale and the ambition of this research, I mean, it really cannot be overstated.
No, it's huge.
They're looking at the direct longitudinal link between visceral adipose tissue, which we'll probably just refer to as VAT for short today.
Right, VAT, that deep belly fat.
Exactly. The link between that VAT and long-term brain health, cognitive decline, and literally the physical atrophy of the brain inside the skull.
So the mission for our deep dive today is to really decode this multi-year, highly complex study for you listening at home. We're going to unpack why losing visceral fat isn't just some cosmetic goal.
It has absolutely nothing to do with bathing suit season.
Right, zero.
No.
It is quite literally about preserving the physical volume of your brain and protecting your memory for decades to come.
Which is arguably the most important thing you can protect.
Exactly. Okay, let's unpack this, because to really understand how fat affects the brain over time, we have to understand how this unprecedented study was even built.
Yeah, the methodology here is key.
Because looking at their methodology, it feels a bit like they built a longitudinal time machine.
That is actually a highly accurate way to frame it. I mean, to measure structural changes in the brain and metabolic changes in body fat over a long period, you need a very specific type of data.
Data that's usually hard to get, right?
Not just hard. It is notoriously difficult, incredibly expensive, and honestly, a logistical nightmare to capture.
I can imagine.
Because, most scientific studies you read about in the news, they take a snapshot, they look at a group of people on, say, a random Tuesday in 2024.
Right. They take some measurements and that's it.
Yeah, they measure their brains, they measure their waistlines, and they look for a statistical correlation. That is cross-sectional data. It only tells you what is happening at one exact frozen moment in time.
Right. So it's a snapshot. You get a picture, but you don't get to see the movie.
Precisely. You don't actually know this sequence of events.
Like you don't actually know if the belly fat caused the brain to shrink, or, I don't know, if the brain shrank first for some other reason and that changed the person's eating habits.
Exactly. Or if they just happen to exist in the same body at the same time by pure coincidence. You just don't know without that timeline.
So how did the FIT project fix that? How did they see the movie?
Well, to see the movie and establish the true long-term biological consequences, you need longitudinal data. And what these researchers did with the FIT project is nothing short of heroic in the clinical trial world.
Heroic is a strong word, but yeah, it fits here.
They essentially went back in time. They tracked down participants from 4 previous highly controlled dietary trials that happened years ago.
Okay, what were those original trials?
So these were the Direct trial from 2005, the Cascade trial from 2010, the Central trial from 2012, and the Direct Plus trial from 2017.
Wow. Just reading those dates out loud gives you a real sense of the sheer timeline we're dealing with here.
It's massive. And the original interventions were these intense lifestyle and diet modifications that lasted anywhere from 18 to 24 months.
Right, so these people were tightly monitored for a year and a half to 2 years.
Yeah. But the wild part is the FIT project caught up with these exact same people between 5 and 16 years after those diets ended.
Which is just crazy. I mean, 16 years later.
Yeah. Tracking people down after a decade and a half is incredibly rare. I mean, people move, they change phone numbers, they just lose interest in science, or unfortunately, they pass away.
So how many did they actually manage to find?
Out of 881 eligible participants from those original trials, this team managed to find and comprehensively assess 599 of them years later.
That is a staggering retention rate for that amount of time.
It really is. And for the specific brain MRI structural analyses we're going to focus on today, they had an N value of 533 participants.
Okay, let's talk about those 533 people so you, listening at home, have a mental image of who we are actually looking at.
Good idea. Context is important here.
Yeah. So this is a predominantly male cohort, right? About 86% men.
Yes, heavily male.
And the average age at the time of this long-term follow-up was 61.4 years old. Their average BMI was around 30.1.
Right, which puts them right on the border of overweight and obese classifications.
Got it. And they had an average waist circumference of about 102.5 centimeters.
Now, it is also crucial to understand why these specific individuals were recruited into those original trials decades ago.
Right, they weren't exactly athletes.
Far from it. They weren't perfectly healthy marathon runners. They were selected precisely because they had underlying metabolic issues to begin with.
Like what kind of issues?
They had long-standing obesity, dyslipidemia, type 2 diabetes, or coronary heart disease.
Okay, just so we're on the same page. Dyslipidemia is essentially when your blood lipids, like your cholesterol and your triglycerides, are completely out of whack.
Yep. That's a good way to put it, yeah.
Like you have high bad cholesterol and low good cholesterol.
Yes, that is the core of it. It represents a serious imbalance in the lipids circulating in your blood, which is, a major driver of cardiovascular disease.
So this cohort represents the very real, very common metabolic struggles faced by a huge portion of the aging global population today.
Exactly. We are looking at what a standard Western metabolic profile actually does over time.
But the truly wild part to me is how they actually looked at these participants when they brought them back in.
Yeah, the technology they used was state-of-the-art.
Right, because they didn't just ask them to step on a scale, take their blood pressure, and fill out a memory crossword puzzle.
Right.
How exactly did they measure the physical changes in these people?
They utilized advanced neuroimaging. They put the participants into 3 Tesla MRI scanners.
Okay, 3 Tesla. That sounds impressive, but what does it actually mean?
To give you some context, a 3 Tesla MRI is an incredibly powerful diagnostic tool. It generates a magnetic field roughly 60,000 times stronger than the Earth's natural magnetic field.
60,000 times! That's insane!
It is. And this massive magnetic power allows researchers to capture these exquisitely detailed, high-resolution, 3-dimensional images of soft tissues inside the body.
Okay, so they scanned their abdomens to map out the fat, and then they scanned their heads to look at the brain.
Exactly. They got full 3D maps of both areas.
But when you have 533 extremely detailed 3D maps of human brains, you can't just have a scientist sit there with a magnifying glass trying to eyeball if the brain looks a little smaller than it used to, right?
Oh, far from it. Human error would be way too high. To analyze the brain scans, they fed the raw MRI data into a fully automated, FDA-cleared volumetric analysis software called NeuroQuant.
NeuroQuant. Man, that sounds like something straight out of a sci-fi movie. What does it actually do?
It is a remarkable piece of artificial intelligence in medical imaging. The software takes the 3D map of the brain and automatically segments it into its constituent anatomical parts.
So it basically slices it up virtually.
Yes, it isolates the total brain volume, the gray matter, the white matter, the fluid-filled ventricles, the hippocampus.
Wow, just pulls all those different pieces apart digitally.
Right. Then it calculates their exact volumes down to the cubic millimeter and adjusts those numbers relative to the total size of the inside of the person's skull.
Their intracranial volume,
Yeah.
right? Because big people have big heads.
Exactly. You have to adjust for head size. This AI approach completely removes human bias and provides an absolute, mathematically precise measurement of brain structure.
So we have this massive 16-year timeline We have massive magnets pulling high-res images and AI-driven brain segmentation.
It's the gold standard of study design.
Which leads me to a question, really. Why bother tracking these people down so many years after their diets ended?
It's a fair question.
I mean, if they were on a strict Mediterranean diet for 18 months back in, say, 2012, what does an MRI scan in 2026 really tell us that a scan at the end of their diet wouldn't have already told us?
Well, what's fascinating here is that the consequences of metabolic health are rarely immediate.
Right, it's a slow burn.
Exactly. Biological changes, especially things like brain atrophy, cognitive decline, and neurodegeneration, these are slow, insidious compounding processes.
Yeah.
They literally take decades to physically manifest.
Like water carving a canyon, you don't see the rock disappear in a single day.
Exactly like that. If you only look at the end of an 18-month diet, you might see some weight loss on the scale. You might see improved fasting blood sugar.
But you won't see the brain shrink yet.
Right, you won't necessarily see the long-term structural changes in the brain. The human brain has a tremendous amount of cognitive reserve. It can compensate for early damage for a long time.
Wow, okay.
By waiting 5 to 16 years, the FIT project acts as a time-lapse camera, showing us the permanent biological consequences of fat exposure over a highly significant portion of a human lifespan.
And that brings us to a mathematical concept they used in the paper that I really want to make sure we nail down for the listener today because it's central to basically everything that follows.
The area under the curve, yes.
Exactly. The area under the curve, or AUC, for fat exposure. What is that?
The AUC is a brilliant metric for a study like this. In pharmacology and medicine, area under the curve is just a way to measure total exposure to a substance over time.
Okay, so how does that apply to fat?
Think of it like calculating your total radiation exposure or your sun exposure. It is not just about how bright the sun happens to be today when you step outside.
Right.
It's about how many total hours you spent baking in the sun over the last 5 consecutive years.
So it's cumulative. It's the total running dosage of fat your body has been carrying and basically enduring.
Yes, the researchers had the MRI measurements of the participants' abdominal fat at the start of the original trials. They had measurements at the end of the 18-month dietary interventions, and then they had the measurements years later at the FIT follow-up.
So they have these 3 distinct points in time.
Exactly. And by mapping those points on a graph, they could calculate the total dosage of visceral fat the participants were subjected to across an entire decade.
Okay, so they aren't just saying, oh, hey, you happen to have a lot of fat today and your brain happens to be small today.
No.
They are saying you carried this very specific measured burden of fat continuously for 10 years, and here's exactly what that decade of exposure did to the physical architecture of your brain.
Yes. It shifts weight from being this static state of being into an active, ongoing exposure event.
That is a completely different way to think about weight. It's an exposure event. That's wild.
It really reframes everything.
So now that we understand the massive scale of how they measured these participants, we really need to dig into what they were actually measuring.
Because the what is the most important part.
Yeah, because this study completely upends the traditional view of body fat. We need to look at the geography of fat and why the where matters so much more than the how much.
Right. When the general public talks about fat or adipose tissue, we tend to treat it as a single uniform substance. Fat is just fat.
Right, it's just padding.
But biologically, adipose tissue is highly diverse, and its function changes radically depending on where it lives in the body. The MRI scans in this study were programmed to distinctly measure 3 specific, separate types of abdominal fat.
Okay, let's map this out for everyone. First, there's superficial subcutaneous adipose tissue, or superficial SAT.
Yes, superficial SAT.
That is the fat located just under your skin. If you pinch your belly or the back of your arm or your thigh, you are mostly pinching superficial SAT.
Correct. Then, moving deeper, there is deep subcutaneous adipose tissue, or deep SAT.
Okay, how is that different from superficial?
This is still a layer of fat beneath the skin, but it is deeper down, structurally separated from the superficial layer by a thin membrane of connective tissue called the fascia superficialis.
Got it. And then we breach the abdominal wall and we find the main character of our deep dive today. Visceral adipose tissue, or VAT.
Yes, the VAT. This is the deep belly fat.
So this is not under the skin. You cannot pinch it.
No, You can't. It is packed deep inside the abdominal cavity, physically wrapping around and infiltrating your internal organs. We're talking about your liver, your pancreas, your intestines.
And the critical, truly alarming finding of this paper is that not all fat is created equal when it comes to the brain.
Not even close.
When the researchers ran their models looking for associations with brain health, cognitive function, and brain atrophy, only the VAT, that deep, unseen, visceral fat, showed a destructive longitudinal relationship.
This is huge. The researchers found that reductions in the deep and superficial subcutaneous fat, the fat you can see in the mirror, the fat you can pinch,
Yeah.
those were practically irrelevant to the brain. They were not associated with better brain structure outcomes years later. Only the presence or loss of the deep visceral fat predicted what happened to the brain.
To take it a step further, and this really challenges our daily assumptions about health metrics, overall, BMI did not significantly predict these brain structural changes either.
That's right, BMI was not the predictor.
When the researchers ran the statistical models and substituted traditional body mass index for the specific VAT measurements, the strong associations with brain preservation completely vanished.
It vanished entirely.
I want to use an analogy here because distinguishing these VATs was a massive light bulb moment for me when I was reading this study.
Oh, please do. Analogies are great for this.
Okay, so if your body is a car, the subcutaneous fat, that superficial pinchable fat on your arms or legs, is basically like a bunch of packing peanuts stuffed into the trunk.
Packing peanuts, okay. I can picture that.
Right. It might slow the car down a little bit because it adds overall weight. It certainly changes how the car looks on the outside, but it's biologically inert.
Yeah, doesn't do much.
It's just sitting there in the trunk, taking up space and jiggling when you hit a bump. But visceral fat, the VAT, that is not packing peanuts.
No, definitely not.
VAT is like having a container of highly toxic, corrosive sludge sitting directly inside the engine compartment right next to the spark plugs, the alternator, and the fuel line.
That's a vivid image.
And it's not just sitting there. It is actively leaking corrosive chemicals into the engine block while the car is actually running.
That is actually a highly scientifically accurate analogy. We used to think of all fat as merely an energy storage depot, a passive biological battery for times of starvation.
But we know better now.
We do. Visceral fat is a highly metabolically active tissue. In many ways, VAT acts like an independent rogue endocrine organ.
A rogue organ. That is terrifying terminology. What exactly is this rogue organ actively doing to the body?
It is continuously pumping out a vast array of biochemical signals. Specifically, VAT is notorious for secreting high levels of pro-inflammatory cytokines.
Cytokines, okay.
Yeah. Cytokines are small signaling proteins that mediate and regulate immunity, inflammation, and blood cell production. We are talking about highly disruptive molecules like interleukin-6, or IL-6, and tumor necrosis factor alpha, or TNF-alpha.
Which is basically broadcasting a chemical alarm signal to the whole body, telling the immune system that there is catastrophic damage, even when there isn't.
Exactly. It promotes a state of chronic, low-grade systemic inflammation. Your immune system is constantly slightly activated, reacting to a threat that is actually just your own fat tissue.
So your body is essentially fighting itself.
Yes. And here is how the toxic sludge from the engine block reaches the driver's seat, which is the brain. These inflammatory mediators don't just stay localized in the belly.
They don't?
No, they are secreted directly into the portal circulation and enter the systemic bloodstream. They travel all the way up to the skull.
Hold on, I have to jump in here. I thought the brain had a defense mechanism against this. Isn't the blood-brain barrier supposed to be this, impenetrable evolutionary fortress?
It is supposed to be, yes.
How does belly fat manage to break down a wall that was designed to keep the brain safe from all the chaos of the bloodstream?
It is a fortress under normal conditions. The blood-brain barrier is a highly selective, semi-permeable border of endothelial cells that prevents solutes in the circulating blood from non-selectively crossing into the extracellular fluid of the central nervous system.
Okay, so it's a tight border.
Normally, yes. However, chronic systemic inflammation is like a continuous years-long siege on that fortress. Over time, those inflammatory cytokines, the TNF-alpha and IL-6 we just talked about, they weaken the tight junctions between the endothelial cells.
Ah, I see. So the mortar between the bricks starts to crumble.
Exactly. The barrier becomes slightly permeable. It becomes, quote-unquote, leaky.
Leaky brain. Yikes.
Yeah. And once these VAT-derived cytokines breach the barrier and enter the brain parenchyma, they induce widespread neuroinflammation.
Inside the brain itself?
Yes. The brain's own immune cells, called microglia, become chronically activated. This direct inflammatory environment severely impairs synaptic plasticity.
Which is what exactly?
Synaptic plasticity is the physical ability of your neurons to strengthen or weaken their connections, which is literally how you learn and adapt.
So the brain basically loses its flexibility. It gets rigid.
It does. And worse, it actively interferes with neurogenesis, which is the creation of new neurons, particularly in the memory centers. It directly threatens the survival of existing neurons and accelerates the degeneration of the myelin sheath that protects your white matter.
That is just awful.
It is a slow, methodical chemical assault originating from the gut and ending in the structural degradation of the skull.
So if you are listening to this right now and you've been stressing over a little extra padding on your hips or the back of your arms, you can honestly take a deep breath.
Yes, don't panic about that.
That pinchable subcutaneous fat is not the villain in the story of cognitive decline. This is purely about the deep, hidden internal fat.
Right, the stuff you can't even see.
It means that measuring your waist circumference with a simple tape measure is a far, far better vital sign for your brain's future than the overall number on a traditional bathroom scale.
That is the absolute essential clinical takeaway from this section of the paper. Two individuals can step on a scale and weigh exactly the same. They can have the exact same BMI down to the decimal point. Yeah. But if person A carries their excess weight subcutaneously in their lower body, like the classic pear shape, and person B carries their weight viscerally, packed tightly around their organs, resulting in a hard, protruding belly.
Then what?
Then person B is in a vastly different, highly elevated biological risk category for severe neurodegeneration.
Which brings us to a massive finding in this paper that honestly completely flipped my understanding of brain health.
Oh, the paradox. Yeah, this part is fascinating.
Because we know the villain is visceral fat. But the researchers didn't just ask if VAT harms the brain. They asked exactly who it harms the most.
Yes. And that led to a discovery that the paper outlines, which we'll call the healthy brain paradox.
To understand the paradox, we first have to understand how they measured cognitive function.
Right, they used the MoCA.
Yeah, during the long-term follow-up, the researchers administered the Montreal Cognitive Assessment, commonly referred to as the MoCA.
For those who haven't heard of it or taken it, the MoCA is a widely used standardized screening tool for detecting early cognitive impairment.
It's a 30-point test, right?
Yes. It asks you to do things like short-term memory recall of a list of words, visuospatial abilities.
The famous one is asking you to draw a clock face and set the hands to a specific time, right?
Exactly. It also tests attention, concentration, and working memory. A normal, healthy score is typically considered to be 26 points or above.
So the researchers ran sophisticated cross-sectional analyses looking for interactions between a person's visceral fat volume, the physical volume of their brain from the MRI scans, and their actual cognitive performance on the MoCA.
Right. They wanted to know, does the physical size and structure of your brain change how much VAT affects your day-to-day cognition?
Here's where it gets really interesting. They found a significant negative interaction between VAT and multiple brain volume metrics.
Like total brain volume, gray matter, white matter, and the hippocampal occupancy score.
But the paradox is the direction of this interaction.
Yes. Let's break down exactly what the data showed. The researchers stratified all the participants into 3 groups based on their total brain volumes. So you have low brain volume, mid-brain volume, and high brain volume.
Okay, makes sense.
When they plotted the relationship between the amount of visceral fat and the resulting MoCA cognitive scores, they found that the inverse relationship, meaning more visceral fat, directly equaling worse cognitive scores, was most pronounced in individuals with mid or high brain volumes.
Wait, I have to push back here because that sounds entirely backwards.
It does, initially.
Wouldn't we logically expect the most damaged brains, like the people in the low volume group whose brains have already shrunken, to be the most vulnerable and fragile to the toxic effects of extra belly fat?
You would think so, yes.
Why would having a larger, supposedly healthier brain make you more susceptible to the cognitive damage of VAT?
It does seem counterintuitive, and it certainly surprised many when reading the initial data.
Oh.
But biologically, when you look at the progression of neurodegenerative disease, it makes perfect sense.
Okay, explain it to me.
We have to consider what we call a floor effect. If an individual already has a low brain volume, it means massive, significant structural atrophy has already occurred over the previous decades.
So the damage is already done.
Exactly. The physical architecture of their brain has already deteriorated.
So they've already taken the hit.
Yes. In those individuals, their MACA scores were consistently low across the board, regardless of whether they had a little bit of visceral fat or a massive amount of visceral fat.
Oh, I get it.
The sheer structural loss of neurons is already the dominant driving force of their cognitive impairment.
Ah, I see. The house is already burned down. Throwing another match on the ashes, like adding more VAT-driven inflammation, it doesn't change the fact that the house is gone.
That's a perfect analogy.
The cognitive score is already bottomed out by the permanent structural loss. You basically can't burn down a house twice.
That's a highly helpful way to visualize it. The baseline structural, vascular, and metabolic factors have already permanently compromised their cognitive performance.
But what about the other groups?
Well, if we look at the participants with high or mid brain volumes, their houses are still largely intact.
They still have a roof and walls?
Exactly. Their neural architecture is relatively preserved. They have healthy synaptic connections to lose.
And so in those intact houses, the matches thrown by the visceral fat, the cytokines, the inflammation, those actually catch fire.
Yes, they do.
You can see the cognitive damage happening in real time on their memory tests because they actually have further to fall.
If we connect this to the bigger picture, the profound underlying implication here is that VAT-related cognitive impairment precedes overt structural neurodegeneration.
Wow. Let me just repeat that so it really sinks in for everyone listening. The cognitive impairment, like the brain fog, the forgotten words, the failing memory, that happens before the brain physically shrinks.
That is the core revelation. The visceral fat is launching a biochemical attack on the brain, while the physical structure still appears relatively healthy on an MRI scan.
So it's a silent attack?
Absolutely. It disrupts the synaptic function, the delicate chemical signaling between neurons, and the overall efficiency of the neural networks long before it literally causes the brain tissue to die, collapse, and shrink.
That is both terrifying because the damage is essentially invisible, but also incredibly hopeful.
Hopeful, yes. Why do you say that?
Because it proves that visceral fat is a massive early warning indicator. It means that if you have high VAT but your brain is still structurally sound, you are currently in the window of opportunity.
Exactly. The window hasn't closed.
The smoke alarms are going off, your cognitive function might be slightly dipping, but the house hasn't burned down yet. It is a highly modifiable risk factor right up until it's just too late.
It completely highlights the particular vulnerability of individuals with early metabolic insults. It dictates a change in clinical timing.
Meaning doctors need to act sooner.
Exactly. It means doctors cannot wait for structural brain changes to appear on a scan before they intervene. By the time the brain volume has significantly dropped into that low category, the severe cognitive impairment is baked in.
So when is the right time?
The critical time to intervene is when the visceral fat first begins to accumulate around the organs, while the brain volume is still in that mid to high protective category.
Okay, so we've established that VA attacks function early, before the structural damage is permanent. But eventually, if left unchecked, if the diet doesn't change and the fat remains, that structural damage does inevitably happen.
Unfortunately, yes, it does.
And the FATI project didn't just measure the brain at the very end of the 16 years. They actually had rolling longitudinal MRI data for a subset of participants from the Direct Plus trial at 3 distinct points in time.
Right? They measured at baseline, 18 months, and 5 years.
So what does that physical attack actually look like over time? Let's move to the physical anatomy of the shrinking brain, which essentially acts as an atrophy accelerator.
When the research team looked at the physical trajectory of brain changes over those continuous 5 years, the anatomical results were striking.
Striking how?
They utilized that area under the curve metric we discussed earlier, the cumulative running exposure to VAT over time. And they found that a higher cumulative VAT dosage predicted a significantly faster rate of brain atrophy.
It's not just that the brain ends up smaller, it is actively shrinking at an accelerated speed year over year.
Yes, the pace of the shrinking speeds up.
And they identified specific anatomical victims within the skull that were taking the brunt of this accelerated decay.
First, they looked at gray matter. To provide some context, gray matter is the darker tissue of the brain and spinal cord, consisting mainly of nerve cell bodies and branching dendrites.
Right.
It is essentially where the processing is done, where synapses are located. It's the raw computing power of the human brain.
So what happened to it?
The studies show that total gray matter volume decreased significantly faster over the 5 years in participants who carried a higher cumulative VAT burden.
The actual computing power is actively eroding away just because of gut fat. That is wild.
It is. Next, they zoomed in on the hippocampal occupancy score, or HOC.
Okay, the hippocampus.
The hippocampus is a small, complex, seahorse-shaped structure embedded deep within the temporal lobe of the brain. It is absolutely crucial for learning, for spatial navigation, and perhaps most importantly, for the consolidation of new memories.
It's the memory center.
Yes. It is often one of the very first regions of the brain to suffer catastrophic damage in Alzheimer's disease. And again, the data was clear. A higher VAT burden meant the hippocampal occupancy score declined at a much faster rate.
So the memory center is literally withering away faster. But there was another anatomical change they measured, right? One that didn't shrink but actually grew.
Yes, there was.
And this is a bit grim, but it's important to visualize to really grasp the physical reality of cognitive decline. They measured the total ventricles.
The ventricles are a connected network of communicating cavities located deep within the brain parenchyma.
And they're filled with fluid, right?
Yes, they're filled with cerebrospinal fluid. Their primary function is to produce and circulate this fluid, which cushions the brain against trauma, provides buoyancy, and helps clear out metabolic waste.
But the studies showed that the ventricles expanded at a faster rate in people with high visceral fat.
Correct, they got bigger.
Now, if you are listening to this, you might logically think, expanding brain parts. That sounds like growth. Isn't growth inside the brain a good thing?
It sounds like it should be.
But I'm going to give you another analogy to explain why ventricular expansion is actually a terrible, terrible sign.
Go for it.
Imagine your skull is a fixed, solid bone box filled with tightly packed dirt. That dirt is your brain tissue, your gray and white matter. Deep inside the dirt, there are small underground lakes of water. Those are the ventricles.
That's a highly illustrative way to look at it because the skull is indeed a closed compartment that absolutely cannot change size once we reach adulthood.
Right, the skull is rigid. So if the dirt, the brain tissue, starts to erode, die off, and waste away, what happens to the empty space left behind?
Nature abhors a vacuum.
Exactly. As the brain tissue atrophies and shrinks inward, those underground lakes, the fluid-filled ventricles, have to physically expand outward.
To fill the gap.
Right. They act like a sinkhole, filling the empty void left behind inside the skull by the dying tissue.
And that is exactly the mechanism at play. Ventricular expansion is a classic, hallmark radiological sign of generalized brain atrophy.
So it's not real growth.
No, it is not that the ventricles are actively growing new, healthy tissue. It is that the surrounding brain tissue is dying and pulling away, allowing the fluid-filled spaces to passively balloon outward.
Man.
And this study definitively showed that the speed of that sinkhole expanding was directly, mathematically tied to the total dosage of visceral fat the person carried over those 5 years.
To put some sobering context on just how real these impacts are to the people actually experiencing them, let's look back at the average MoCA cognitive score for this cohort at the end of the follow-up.
Okay, let's look at the numbers.
Out of a perfect 30, the average score across hundreds of participants was 23.6.
Yes. And as we established earlier, a normal MoCA score indicating healthy cognition is 26 or above.
So they were well below normal.
A score of 23.6 firmly places the average participant in this specific study in the clinical range of mild cognitive impairment, or MCI.
The authors of the paper explicitly note that an average of 23.6 is relatively low for a group whose average age is only 61.4.
Right, that's young for that kind of decline.
In the grand scheme of human lifespans, 61 is just late midlife. You would not expect an entire cohort of early 60-somethings to be hovering collectively in the mild cognitive impairment range.
It is significantly lower than expected for the general population at that specific age bracket. But well, when you extrapolate the context of who these people are and what their bodies have been through, it makes total biological sense.
How so?
Remember their baseline characteristics. They were recruited into these dietary trials because they already possessed long-standing obesity, dyslipidemia, and type 2 diabetes.
So they had a history.
Yes, they had been carrying heavy metabolic burdens for decades.
So what we are looking at isn't just an abstract spreadsheet of data. This is a real-world clinical manifestation of what metabolic syndrome does to the human brain over the course of decades.
Exactly. It accelerates everything.
It pulls cognitive decline forward in time. It makes a 61-year-old brain function like a much, much older brain.
It clearly demonstrates that metabolic disease is not just a cardiovascular issue to be managed by a cardiologist. It is a profound neurological risk factor that fundamentally alters the aging timeline.
Wait, if these toxic cytokines are pooling in the belly and the brain is all the way up in the skull behind the blood-brain barrier, How is that sludge actually traveling upwards to cause this specific pattern of accelerated atrophy?
That's the million-dollar question.
We talked about the leaky blood-brain barrier, but what is the primary vehicle of destruction here? What is the mechanism actually driving it?
To answer that, the researchers conducted what are called sensitivity analyses. They were essentially hunting for the proverbial smoking gun.
Okay, what were they looking at?
They had a massive wealth of biomarker data on these participants from the very beginning of the trials.
Yeah.
We're talking detailed blood tests, measuring their cholesterol, their triglycerides, their various inflammatory markers, and their blood sugar profiles.
So they wanted to see which of these baseline biomarkers actually interacted with time to predict the fast trajectory of brain changes.
Exactly.
Basically, if we line all the biological suspects up in a police lineup, which one is actually holding the weapon that shrinks the hippocampus?
And the results of this lineup were fascinating, largely because of what didn't cause the primary damage.
Right, what didn't cause it?
When they tested the lipid markers, things like LDL cholesterol, HDL cholesterol, and total triglycerides, they did not show consistent, statistically significant associations with longitudinal brain atrophy over time.
Really? Cholesterol wasn't the main culprit.
No, it wasn't. And even more surprisingly, given what we just talked about with the cytokines and the rogue organ theory, the baseline systemic inflammatory markers, specifically high-sensitivity C-reactive protein, or hsCRP, also did not show consistent associations over the long term.
So inflammation and cholesterol aren't the smoking guns. Then what is?
Two specific biomarkers emerged as the absolute winners, the clear, undisputed drivers of the atrophy trajectory:
And they are.
fasting glucose and HbA1c.
Fasting glucose is exactly what it sounds like, right? The measurement of how much raw sugar is floating in your blood after you haven't eaten for at least 8 hours.
Correct.
And HbA1c, or hemoglobin A1c, is a marker that measures how much sugar is attached to your red blood cells, giving doctors a 3-month average of your overall blood sugar levels.
Yes, those are the ones.
They are the classic gold standard markers of insulin resistance and type 2 diabetes.
What the researchers discovered here is a vital pathway we can call the glycemic bridge.
The glycemic bridge.
Visceral adipose tissue is notoriously intimately linked to the development of profound insulin resistance. VAT secretes high levels of free fatty acids and specific hormones like resistin that actively block the action of insulin in your skeletal muscles and your liver.
I want to make sure everyone understands insulin resistance because it gets thrown around a lot in the health space.
Yes, it's a very common term. Let's define it.
I like to think of insulin as a key, and the cells in your body are a door. When you eat, sugar enters your blood, and insulin acts as the key to unlock the cell door so the sugar can go inside and be used for energy.
That's a great baseline understanding.
But insulin resistance is like the lock on the door getting completely rusted out.
That is an excellent way to conceptualize it. The lock is busted.
So the body produces more and more insulin, frantically trying to jam the key into the rusted lock, but the door won't open.
And what happens to the sugar?
All that sugar has nowhere to go, so it just stays stranded out in the bloodstream, continuously elevating your blood sugar levels.
Exactly. It just builds up.
But how does that rusted lock in the muscles build a bridge of damage all the way up to the brain?
When chronic insulin resistance and chronically elevated blood sugar occur, it causes profound vascular dysfunction throughout the entire body. The delicate single-cell lining of your blood vessels, known as the endothelium, becomes severely damaged by the high glucose environment.
Like having a microscopic shards of glass scraping the inside of a garden hose.
Yes, exactly. The high sugar environment creates advanced glycation end products, which literally stiffen and damage the vessels.
And in the brain.
In the brain, this manifests as microvascular damage. The tiny microscopic capillary networks that feed your individual neurons become stiff, occluded, and incredibly inefficient.
So the brain is essentially being slowly, methodically starved of its optimal blood flow.
It is a slow suffocation. Impaired cerebral blood flow means the brain cells aren't getting the constant supply of oxygen and metabolic nutrients they require to maintain their complex structure.
That seems disastrous.
It gets worse. Furthermore, insulin resistance doesn't just happen in the muscles, it happens in the brain itself. And insulin signaling in the brain is required to power the brain's garbage disposal system, known as the glymphatic system.
Which clears out metabolic waste.
Yes, it clears out neurotoxic proteins.
You mean proteins like the beta amyloid plaques and tau tangles that build up in Alzheimer's disease?
Precisely. In a healthy brain, robust insulin signaling helps regulate the clearance of these harmful byproducts of cellular metabolism.
But if the brain is insulin resistant,
When the brain becomes insulin resistant due to the cascading effects of visceral fat, the garbage disposal system breaks down. The toxic amyloid proteins accumulate, the microvessels are damaged by the high sugar, the oxygen levels drop, and the neurons begin to physically die.
that is the glycemic bridge.
Yes, that's it.
It travels from the insulin-blocking visceral fat in the belly through the sugar-damaged microvessels in the blood, all the way up to the shrinking hippocampus in the skull.
This raises an important question. A massive paradigm-shifting question, really, about how the medical community views dementia.
That's the question.
Are we looking at this entire category of disease wrong? Should we be looking at cognitive decline and diseases like Alzheimer's, not just as mysterious, unpreventable neurological diseases that strike out of nowhere as we age, but as chronic, long-term metabolic diseases?
I mean, some prominent researchers in the field are already referring to Alzheimer's disease as type 3 diabetes
They are, yes.
because the insulin resistance in the brain is so profound.
It is arguably one of the most vital debates in modern neurology right now. This specific study adds immense longitudinal weight to the argument that metabolic dysregulation, driven specifically by visceral adiposity and resulting in poor glycemic control, is a foundational root cause of neurodegeneration.
So if it's metabolic, we can treat it differently.
If we officially view cognitive decline as a metabolic disease, it completely revolutionizes our approach to treatment and prevention.
Hmm.
We move away from solely trying to develop billion-dollar pharmaceutical drugs that try to retroactively scrub plaques out of the brain.
Which historically haven't worked very well anyway.
Exactly. And we move toward therapies that fix the metabolic engine in the body decades before the plaques ever form.
Which brings us to a crucial turning point in this deep dive. Because if we stopped right here, this would just be an hour of totally terrifying biology.
Yeah, we'd just be scaring people.
We've covered a staggering amount of alarming data about toxic sludge, shrinking gray matter, rusted insulin locks, and expanding sinkholes in the brain.
It's a lot of doom and gloom.
But the central premise of the FIT project, the reason it is published in a journal as prestigious as Nature Communications, is actually one of profound, actionable hope.
The core fundamental question they ultimately sought to answer was this. If visceral fat causes the structural damage to the brain, does losing that visceral fat actively stop the damage?
Can we fix it?
Can we hit the brakes and reverse the trajectory?
Let's talk about the silver lining, because it is incredibly bright. In the original 18-month randomized controlled trials, specifically looking at the central and direct plus cohorts, the participants were put on highly structured lifestyle and dietary interventions.
And they were closely monitored.
And they were wildly successful. On average, the participants lost a remarkable 24% of their visceral adipose tissue during that initial 18-month period.
Losing nearly a quarter of your visceral fat depot is a massive metabolic achievement. It completely changes the inflammatory profile of the entire body.
But did it help their brains?
Well, the researchers didn't just want to know if they lost the fat. They wanted to know what that specific, targeted fat loss did to the physical architecture of their brains a full decade later.
And here's the monumental finding. A greater reduction in visceral fat during those brief 18 months was directly associated with a significantly higher total brain volume, a higher gray matter volume, and a higher hippocampal occupancy score 5 to 10 years later at the FIT follow-up.
It is a stunning long-term validation of the intervention. The individuals who successfully mobilized and burned off their visceral fat during the diet phase essentially bought themselves a larger, more intact, more youthful brain a decade later.
They fundamentally altered the trajectory of their own aging.
They absolutely did.
And crucially, and I really want everyone listening to hear this loudly and clearly, changes in overall BMI during the intervention did not associate with these preserved brain structures years later.
No, BMI didn't matter.
Losing general weight on the scale didn't guarantee a bigger brain. Losing the deep visceral fat guaranteed the bigger brain.
It perfectly reinforces everything we discussed about the geography of fat. If a participant lost a significant amount of weight, but it was mostly subcutaneous packing peanuts, their brain did not reap the long-term neuroprotective benefits.
Because the packing peanuts weren't hurting the brain to begin with.
Exactly. The specific targeted depletion of EAT is what silenced the inflammatory alarms, repaired the glycemic bridge, cleared the microvessels, and ultimately saved the neurons.
So what does this all mean? Let's bring it all together for the listener. How exactly did they target this specific fat?
In the original trials, they used highly specific dietary protocols. They primarily utilized the Mediterranean diet, but in the Direct Plus trial, they pushed it further.
What did they do?
They used what they termed a green med diet. This was a calorie-restricted Mediterranean diet that was highly enriched with specific plant polyphenols.
Let's break down the green med diet because it sounds fascinating. They were drinking massive amounts of green tea, and they incorporated a specialized aquatic plant called mankai.
Yes, mankai was a key component.
What exactly is mankai?
Mankai is a specific strain of duckweed. It is an aquatic plant that is incredibly rich in bioavailable protein, iron, and a very specific profile of polyphenols.
So they were eating duckweed.
In the trial, participants consumed a mankai green shake daily, along with eating walnuts, while strictly reducing their intake of red and processed meats.
But how do polyphenols, these compounds from tea and duckweed, actually shrink visceral fat better than just cutting calories? What is the cellular mechanism there?
Polyphenols are powerful phytochemicals. In the body, they have been shown to upregulate fat oxidation, meaning they basically encourage the body to burn fat for fuel rather than store it.
Okay, so they burn fat faster.
More specifically, certain polyphenols can induce something called mitochondrial uncoupling in fat cells, which essentially turns up the metabolic heat and burns off stored energy.
So it's like throwing a log on the fire.
Furthermore, polyphenols have profound anti-inflammatory properties that directly counteract the cytokines produced by VAT. They essentially disarm the rogue organ while simultaneously shrinking it.
Now, as with any scientific deep dive, we have to play devil's advocate. We have to look at the limitations of the study fairly, because no single paper, no matter how massive or well-designed, is perfect.
The authors are commendably transparent about the study's limitations, which is always good to see. First, as we mentioned early on, the cohort is 86% male.
Right, mostly men.
This is a significant caveat. The way men and women store fat and the complex hormonal environments surrounding that fat, particularly regarding estrogen, which is highly neuroprotective premenopause, are very different.
So, while the underlying biological mechanisms of the glycemic bridge likely hold true for everyone, we need more dedicated long-term research to see if the exact same volumetric brain savings occur at the exact same rates in female populations.
Exactly. Another significant limitation is the black box of the follow-up gap.
The black box, what do you mean?
Well, the researchers rigorously controlled and monitored the diets for 18 to 24 months. But then, for the next 5 to 16 years, the participants were out living in the real world.
Oh, right. They couldn't follow them around for a decade.
The researchers couldn't tightly control what they ate, how much they stressed, or how they exercised during that entire decade gap.
They did attempt to adjust for this statistically, right? To filter out some of that real-world noise.
They did their absolute best. They used a validated Mediterranean diet adherence score in all their statistical models to account for the participants' post-trial behaviors.
So that helps smooth out the data.
It helps rule out the possibility that the people with better brains just happen to eat perfectly for 10 years on their own accord. The statistical models strongly suggest the initial 18-month VAT loss had an independent, lasting effect.
But it's still an observational gap.
Right. Observational data over a decade will always have some inherent noise.
And finally, while they used incredible 3 Tesla MRI technology to measure the physical volume of the brain, they did not have access to Alzheimer's-specific biomarker data.
Correct. They didn't have amyloid PET scans or cerebrospinal fluid taps to explicitly confirm if the brain atrophy they were seeing was definitively Alzheimer's disease pathology.
Or if it was just general shrinking.
Or if it was a more generalized, metabolic-driven vascular neurodegeneration. We just can't say for sure.
Though, practically speaking, if your hippocampus is actively shrinking and your memory is fading, the exact biochemical label a neurologist puts on your chart might matter a whole lot less to you than the sheer fact that you are losing your cognitive function.
That's a very fair point.
The outcome, the cognitive impairment, is what we are desperately trying to avoid no matter what name is on it.
To build on that, regardless of the specific pathological label, the loss of gray matter and memory function is a devastating outcome. And this study provides a concrete, highly modifiable, non-pharmaceutical target to prevent it.
So as we wrap up this deep dive into the FIT project, I want to connect this directly back to you, the listener. The next time you think about your metabolic health, or the next time you look at the food on your plate and make a dietary choice, I want you to completely shift your perspective.
Think beyond the waistline.
Exactly. You shouldn't just be thinking about your heart health. You shouldn't just be thinking about how your clothes fit. You need to think about your hippocampus.
The adipose brain axis is a very real very powerful biological superhighway. Your gut and your brain are in a constant, lifelong biochemical conversation.
And the most empowering takeaway from this massive undertaking is that this axis is modifiable. You have the total agency to change the tone of that conversation.
By targeting visceral fat through sustained, polyphenol-rich lifestyle and dietary changes, you aren't just burning calories. You are actively disarming a rogue organ that is pumping neurotoxic signals right into your bloodstream.
You are tearing down the rusted locks of insulin resistance. You are rebuilding the glycemic bridge to your brain.
And I'll leave you with a final, slightly provocative thought to mull over as you go about your day.
Ooh, let's hear it.
If our deep belly fat truly acts as an independent, destructive organ, sending metabolic signals that physically shrink the brain, could the future of cognitive therapy look completely different than anything we've imagined? Could the cure for cognitive decline, the way we protect our memories in the coming decades, lie not in billion-dollar brain training apps or in highly complex neurological drugs that try to scrub plaques out of the skull?
Could the most effective, most powerful intervention for dementia actually be found by looking downward? Imagine a future where highly targeted metabolic therapies, whether nutritional, pharmaceutical, or behavioral, are designed specifically to shrink visceral adipose tissue before the very first memory is ever lost.
Could the cure for cognitive decline actually be found in the gut?
It's a whole new way of looking at the mirror and the scale. That number on the digital screen, it's not the final judgment of your health, it's just the murky surface. It is what's underneath, hidden deep in the engine compartment, that ultimately decides the future of your mind.